Hello everybody. So let's first off address the elephant in the room. So it's been a minute since I've put out a video. A few minutes. The brand was called Cumulus Corp. I've changed it to Cumulus to Lenticular. There's a little rebranding going on there. Cumulus just basically means that I'm building cloud, so as in a student pilot, to lenticular, like a tall standing cloud. The lenticular basically represents an ATPL, but it also represents that the journey never stops, so you're always learning. I'm at about 3,000 hours now, and I'm still learning. There's a lot, and it always will be. So yeah, this is a quick welcome back. So we're gonna jump back into weather. I know weather's been always a very tough subject for a lot of students, myself included, but I do seem to understand it a lot more. I'm no expert. I am using the Aero Command Manual, and through that I break down lessons. My goal is to break it down to make it 10 times easier. Well, I try to make that entertaining somehow. I don't know if it's gonna work. We'll try it, okay? So no big promises, but I have been told I am a somewhat of a okay teacher. So here's to that. Lessons, we will be starting with changes of state, moisture content, dew point, relative humidity, condensation nuclei, and how that affects our aircraft. So those are basically chapter 1 of Aero Command Manual. If you go look into there, everything's on there. I don't make shit up. I just break it down. Simplest question. What's the simplest question? Well, what is moisture? Where does it come from? Why is it even there? So the Earth's surface, from the Earth itself, is about 71% water. That's a lot of water. So that water's got to go there somewhere within our atmosphere. So what happens is evaporation. Evaporation is a natural process because Earth is releasing heat and it's also absorbing heat. Since the Earth's surface absorbs heat, so does the water. When all water absorbs heat, it evaporates. And that evaporation is called, ding, 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 you guessed it, moisture. So that's where moisture comes from. It also comes from vegetation. It also comes from the Earth itself, like the surface. It also comes from us. It usually only hangs around between 20 to 40,000 feet. Nowhere higher. So it goes from surface to about 40,000 feet. It can go higher, however, but that's when the science really gets fun. So that's for a different day, though. That, my friends, brings us to latent heat of vaporization. Well, what is that, you might ask? Well, let's break that down. Latent, all that means is concealed, inactive. You know, doesn't do much. Heat, obviously, that's where all the fun stuff happens. And vaporization is just steam. It's energized water. That's all that is. So now we bring that into the stages of like the solid, liquid, gas we were talking about. Bring that into the stages. And you take vapor to a liquid. Well, here's a great example of that. When you're outside on a hot summer day, now listen carefully. You hear those crackles? There's a process there. So that right there is a great example of latent heat of vaporization, where we talk about the stage of vapor to a liquid. That's exactly what's happening outside of this glass. The air outside is warm, it's moist, and what it's doing is attaching to the glass molecules, and the glass molecules are at a solid stage because this is a solid, but they are being influenced by the cold water and the ice inside. So once those outside molecules hit the surface of the glass and they attach to the glass surface, to its molecules, they instantaneously turn into visible moisture that you can actually see. That, in today's day, we call condensation. And you can see, there it is. You can actually see it on my fingies. The version we can talk about is going from a liquid to a vapor. So that's basically absorbing heat. So you have something that's liquid. Let's put that on a stovetop, right? All those molecules will get accelerated, they'll get excited, then they'll start jumping up, and there you have it. You have boiling water, and that boiling water only makes the molecules of the water excited, and then they jump out, they jump away, they release off into the air. That, in a nutshell, is latent heat vaporization. Simple, right? Nothing too complex. That actually just brings us to the next one, latent heat of fusion. Latent, again, only means concealed or inactive. And fusion just means melt. Two great examples of that would bring us back to a liquid to an ice form, right? So when something's liquid, for example, you take an ice tray, fill it up with water. You take that tray, put it in the freezer. It's releasing the heat, right? And it's melting. So there's a process there. It is releasing the heat and it is becoming a solid. So it's going from a more active state to a less active state. And that less active state causes it to become a ice cube. There you go. Now you got ice cubes for your drink. Maybe a bottle of whiskey. From the ice to a liquid again. So now you bring that ice cube and then you put it on the table. And what happens? Well, that ice cube is going to take all the air around it and all of the heat around it, and we'll take it in because it's cold. So then it changes from that ice cube back to liquid. There you go. That's that process. That is called latent heat of fusion. Brings us to my favorite subject, which is sublimation, latent heat of sublimation. Now, sublimation, all that means is rise or to elevate. The examples of those are when you move from an ice stage straight to a water vapor stage. Think of dry ice being pulled out of the freezer, and as soon as it hits the surface or any sort of hot or cold air, it'll start evaporating instantaneously. And that's basically heat again being released. Now we can think of the opposite of that would be deposition. Well, it's going from water vapor to ice. You know, it's going back to that solid state. Great example of that would be frost, right? On your windshield. When you wake up early morning, there's frost on your windshield. Well, what happened there? Well, overnight, as the temperatures got cooler, the air around the moisture that was in the air got cooler as well. And then it touched the warm surface of the vehicle, so that instantaneously turns into frost. A great example is snowflakes in clouds, right? Inside a cloud, that's exactly what's happening. It's going from that liquid stage and it's getting so cold that it's turning into ice crystals. When those ice crystals form, they attach to each other and that forms a snowflake, and therefore a snowflake falls. And now you have snow. That basically, in a nutshell, is your changes of state. It's going from solid, liquid to gas with the processes we talked about. Again, it's the release or absorbent of latent heat. Directly brings us to moisture content. So take a parcel. That parcel of air, let's give it 10 degrees Celsius. If at 10 degrees Celsius, you start adding moisture to that parcel of air, and you do not move that 10 degrees Celsius, it will get to a certain point where the parcel of air can only hold a limited amount of water, or moisture in this case. And the limit, once that limit is reached, saturation occurs. Saturation is where we actually visibly start seeing the cloud forming. Any cooling further than that will cause condensation or a cloud to form. Therefore, the same process. We're seeing up that mountain slope, we see condensation, that's exactly what will happen in that parcel of air at 10 degrees Celsius. So again, at a certain degree, if you increase the temperature, it will be able to hold more and more water. As you decrease that temperature, it will be able to hold less and less water. And if that confuses you, think of, again, the air molecules. This roots back to my very first video that was posted years ago, where the air molecules, imagine they're just like people. They want to be very close in the wintertime because it's cold, and they want to be very far apart from each other in the summertime, which totally makes sense, right? If we're sweaty, we want to be away from each other so we can get that cooler air between us. So that's exactly what the air molecules want to do. So as they spread out, when the temperature increases, such as, let's think of a tropical place, the air there is very moist. Why is that? Well, it's able to hold that moisture because it's warmer. So since it's plus 30 or 35 degrees there, up here in Canada, for example, when it's plus 10, when it's plus 30 over there, plus 10, it's going to be able to hold a lot less moisture content because those air molecules are closer in. So that space in between each molecule is what takes up the moisture. The moisture takes up that space. So if there's not much space left, boom, you can't hold that much moisture. I hope that makes sense. We relate moisture content and the topic we talked about with the temperatures to really picture this. Think of a cumulus cloud forming. Now, a cumulus cloud is forming because the moisture off of the ground is going up. Now, that moisture is cooling down. As it cools down, it condensates. As it's condensating, it's releasing more heat into the atmosphere. That same heat inside of that cloud is attaching to more water molecules. And as it attaches, it also wants to cool down. That upward process slowly keeps moving up and up and up and further up. If you take a very moist climate and add that same process inside that very moist climate, the clouds will climb up to roughly 40 to 60,000 feet to eventually form into an anvil. And that's where we see anvils. It'll get so high where it can no longer continue. So then it will flatten out. That happens a lot in places like Canada or America. But down south, you will see clouds up to, like I said, 60 to 70, maybe up to 80,000 feet. So in warmer temperatures, that latent heat is going to be a bad news for everybody. Ladies and gentlemen, is a quick wrap to part 1 of the video. The rest of the topics that we have to go over includes, but not limited to, dew point, relative humidity, and condensation nuclei, and how all of these affect our aircraft performance. So thank you for following me, and that is a quick wrap to part 1. I hope you continue for part 2.